Got the paper pinned. So, welcome to Monday, December 14th class session. The only purpose of this class session is to answer your questions, and so I'll do any examples you want. I will first just show you our last week's screen here. Get someone else in the room. So let me share our web page with you for just a second. Math 121. So here's the home page where I'm giving you instructions about exam 2. And basically, instructions are pretty straightforward. You have a homework due tomorrow night by 11:59. And then I will, about that same time, post exam 2. And then you have 48 hours. You'll submit it to our assignments folder by 11:59 on Thursday. I tried not to do too much writing on the exam. I'm not going to show you the exam itself, but there's probably more writing on the instruction page than there is on the exam itself. And in one way, I apologize for that, but I have to keep these records. And if you don't have access to a printer and you have to write out the whole exam, you know, the problems are short. The instructions and your acknowledgement page are a little bit longer. Okay, good. Just throw everything like that into the chat. Thank you. So if you can also throw your questions straight into the chat. So this is not the exam, but this is the instruction page of the exam where I do want your signature and your acknowledgement that you followed these instructions. And again, that is not because I see you not following the instructions. It's literally because in this kind of Wild West atmosphere that we're in, I'm trying to cover you completely in the event of any transfers. What were the conditions that you gave your test on? Some schools can get very particular about accepting transfer credit for online courses. And I know those schools, and I don't know where you might transfer to someday. So I just want to make sure you're covered, and then I have a record of the conditions you took the exam under. That's why. So if you have to write out this page, it's not terrible to write this out, but I didn't want this writing out of this page to take away from your 48 hours. So I've posted that page ahead of time. Okay, other than that, we got our normal office hours this week. There's our assignments folder. Let's pop down to week 16 just so you can see where the exam's going to be released. Right here, there's the instructions. Then I'll post the exam tomorrow night. And when everything is done, I'll post an answer key here if you want to see them. You don't have any written homework due, and your only homework due tomorrow night are these last three sections of the XYZ homework. Then I'll get up all of your graded homework, grade reports, exam 2 graded. I'll scan them, put them back in your Google Drive folder with a final grade report and let you know that it's all there. So that's the program, and it's pretty much the same program as first exam. But now it's just the last week of the semester. Grades I have to turn around pretty quickly. I can't tell you exactly what day or time I'll have them finished, but it'll be quick. It'll be days. It'll possibly be by the following Monday. Okay, so that has got everything I wanted to say. So you tell me what you want to know. And Austin has posted a question. So let's just do it. That's exactly what I want. Just whatever question you want to look at. So I have this equation in rectangular coordinates. X squared plus y squared equals 2x. And you figured out an XYZ, but you want to know how to do it or an efficient way to do it. So let's convert this to polar coordinates. Well, whenever you're going back and forth in polar coordinates, first thing you put on your paper is just your standard right triangle, where you have an X and a Y, horizontal, vertical, radius or hypotenuse R. You can call the hypotenuse R, C, whatever letter you like, D, but common to call it radius R. And then angle theta. And this lets you basically look at that. X and Y, rectangular coordinates, R and theta, polar coordinates. So this is like a key that makes you go back and forth between the two coordinate systems. So if you want to know polar to rectangular, you do such. And if you want to know rectangular to polar, you do such. What about polar to rectangular? Since X over R is cosine theta, X divided by R is cosine theta, but I'll multiply the R immediately over to the other side. Y equals R sine theta. These are the instructions that if you know R and theta, you can immediately know X and Y. The other way, which is what we're interested in a little bit here too, if you know the rectangular coordinates, how do you find the polar coordinates? Well, R squared by the Pythagorean theorem is X squared plus Y squared. Or you could say R is the square root of X squared plus Y squared. I don't mind that either. I just don't like using square root signs when I don't need to. And the theta, you could do lots of things. Sine theta, Y over R, cosine theta, X over R, tan theta, Y over X. Usually people say it like this. The theta, this is usually the most direct way to say it, tan inverse of Y over X. And these are two sets of instructions. Sorry, slide up the paper, but you can use both of them right here. So if I was to convert this to polar coordinates, the first thing I see is the X squared plus Y squared. That is automatically R squared. Then 2 times X, if X is R cosine theta, I just immediately insert R cosine theta into there. I've now written the equation in polar coordinates. That doesn't mean I can't make it simpler, but this equation is now in polar coordinates. Oh, I apologize, I forgot the 2. The 2 was in front of the X. Here's the X right here. What I could do to make this simpler is I've got this extra factor of R here. So, you know, it depends on what words you want to use. Let's divide by R. I always get nervous about that because what if R was 0? Dividing by 0 is illegal. What I could do is say R squared minus 2R, but essentially you're going to end up dividing by R, equals 0. R times R minus 2 cos theta equals 0. Now that, remember, 2 things multiplied together give me 0. Either R is 0, which I was wanting to avoid, or R minus 2 cos theta is 0, which means R is 2 cos theta. So if we exclude R equals 0, which is just the center dot, let's draw this really quickly, because I'll draw it in decimals. R equals 0 is right there. Of course, R equals 2 cosine theta is a circle of diameter 2 on the x-axis. Which also includes that dot. So this point is also in this equation. And so that's why most people, if they were told to convert x squared plus y squared equals 2x, they would just write r equals 2 cosine theta, because the extra r here is redundant. Excuse me. So this would just show up very nicely in Desmos. So let's pop it into Desmos. And while you're working on your exam, you can pop things in Desmos just to check them and stuff like that. Desmos calculates pretty well too, but I got x squared plus y squared equals 2x. You could not type that into your calculator and get that immediate circle. You'd have to draw it nicely for your calculator. You'd have to like solve for y or something. But here it is, diameter 2, kissing the origin, symmetric about the x-axis. But now let's do the polar equation too. R equals 2 cosine theta. I just typed the word cosine, typed the word theta. And I'll let theta go from 0 to, well, they already draw it for me. See, they draw for me in blue. So I could put the dotted, so I got the red curve there. I got the blue dotted curve there. It is the same curve. So we just demonstrated these were the same. Okay, great question. And if you want to convert anything to polar coordinates, this is the key. This is the key for going back and forth between rectangular and polar coordinates. Even if you did not remember, sorry, got to go back to my paper. Even if you didn't remember these formulas, if you remembered that triangle, you can make these formulas. Toss up another question there. I also want to say, I think those formulas are on your formula sheet, but I better check it before I say that. Here's your formula sheet, blah, 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 blah. That's very interesting because I do not see that immediately. I mean, the formulas are right here in that sense that there's the triangle, but I don't see that immediately. Well, make a note of those, make a note of that triangle I just showed you. And I'm not going to say I'm going to add this to the formula sheet before the test because you have everything you want to write down before the test. But if I was in class, I think I'd make sure I would add that to the formula sheet. Don't see it. That surprises me that I didn't have that on there already. Okay. Great start. What else can I do for you? You can type it or say it, whichever one's easier for you. I lost my trash can down here. Sitting in the basement and I lost my trash can. Okay. Stop that wiggling. I'm just straightening up my desk and cleaning up papers. So I don't mind if you just want to hang out. But I don't have anything I'm going to show you other than whatever questions you want to ask. Right now, I'm just finishing reading the last written homework that you gave me so I can have that posted back to you. Among the problems there, you know, everybody does things a little bit differently. But don't forget the 15-degree, 75-degree, 90-degree triangle. Right triangle. And don't forget the ratios of those sides. It's kind of long and thin. I'm not trying to draw it exactly at 15 degrees. I think that's too many degrees. But the ratios of the sides went √6 plus √2 for long side, √6 minus √2 for short side, and 4 for the hypotenuse. But that added a lot of rectangle, that added a lot of triangles to your known triangles. So don't forget that triangle. Understandable, but come back on, and you don't have to leave. I'm not saying leave, but when you come back on Wednesday, remember you will have the exam in your hand and you will know the questions I'm asking, you know, very similar to some questions in the book. So I have no problem if you want to hunt through the exam, go find questions that are similar to the book, and then bring those also on Wednesday. So you do have one more safety valve, so to speak. It is tricky. I understand this right now, like coming to the end of the whole thing, and you know, it's like the old Peanuts cartoon, you know, may I be excused, my brain is full. Yeah. Got too many things in your head right now. I understand that. Squared and cubed roots. Okay, that's very good. That's very good. Let's try it. Let's do the cube one, and I'll come back and do a square one. Because what I got to do for this problem is I got to make a picture in your mind. And once you have the picture in your mind for a cube root one or something else, the square root one won't seem so strange. Okay. Back before you knew complex numbers, If someone said solve this, you would say, oh, I know the answer. 2 and minus 2. If someone said solve this, you would say, I know the answer. It's just 2. Because as far as you knew, there is only one number you could cube to get 8. And that was the number 2. There's no other number on the real number line that you could cube to get 8. But when we added the imaginary axis, or I could say it like this. When we created the complex numbers, we opened the door to more answers. Possibly more answers. And we did it like this. And that pen is running out of ink. So you and I think of 8 as just a real number. That's most of our life we've been thinking like that. But we can also think of 8 as a complex number. Eight plus 0i. Now that's in standard form. But if I drew a picture of it, I'm going to advance my paper. Where this is the real number axis, and this is the imaginary number axis. So 1i, 2i, 3i, 1. Well, let's make this 4 here. 2, 4, 6, 8 right there. And that dot right there is 8, or 8 and no i's. So the real number line is inside the complex plane. So hang out for a second while I draw this, because after I create this picture in your mind, then you'll have it, I hope, permanently. But that was written in standard form. And now from this last chapter, you realize there was another way to write it as distance from the origin and angle from the positive horizontal axis. I can also write 8 times cosine theta plus I sine theta. And in this problem, the theta, the angle from the positive x-axis, positive horizontal axis, is 0. So when I write that 8 plus 0i as 8 cosine 0 plus I sine 0, and that's, right now I'll think degrees, if you like. I think naturally in degrees. that gave me a way to both multiply and divide complex numbers by just using the radius and the angle. If I multiply them, I just do R1, R2, cis theta 1 plus theta 2. If I divide them, I just do R1 divided by R2, cis theta 1 minus theta 2. Let me advance my paper. And now we get to the punchline. If I raise a complex number to a power like n, I get R1n cis n theta. But remember, a root is just a fraction power. So I could take a root by saying z to the 1 over n, which is r to the 1 over n, cis theta over n. Just multiply by 1 over n or divide by n. Now let's see what that does in the case of the cube root of 8. Well, I'll take 8 cosine theta, theta is 0, plus I sine theta, theta is 0 degrees. And I'll take the cube root of 8, which happens to be 2. Slide this up, sorry. Got a little video lag here. And I'll take 0 and divide by 3. And at first you say, well, big deal. That doesn't change anything. 0 divided by 3 is still 0. But the difference is, this is 1 of 3 cube roots of 8. Because if I go back to my picture, and I can get this all in one paper, I don't know why my camera is always shaking. I must be kicking the table. Sorry. That's right here. There's 2 cis 0. And you let me use the abbreviation cis for cosine 0 plus I sine 0. That's an abbreviation. But since I add angles when I multiply a cube, I could also, like the spokes of a bicycle wheel, take 360 divided by 3 to give me 120 degrees. I could also take this number over here with the same radius, but 120 degrees over. And what happens when I cube 2 cis 120? Well, I cube the 2 to give me 8, and I multiply the 120 by 3. I'm using that formula right there. But multiplying 120 by 3 is 360. And cis of 360 is 0 degrees, is exactly 8. So this becomes a new cube root of 8. It's not on the real number line, it's in the complex plane. But if I did it once, I can do it again. Add 120, get a new answer. Add 120, get another new answer. And what's 120 plus 120? That's 240. So what's cis 240 cubed? Well, again, 2 cubed is 8. And 240 times 3 is 720. But 720 is just 0 degrees. This is also 8. So what I get is, I'm going to switch to another paper now, but I'll draw again. I get 3 cube roots of 8, 2 cis 0, 2 cis 120, and 2 cis 240. And they all come from this idea of first you find the first cube root by dividing by n. And then if you're doing cube roots, you do 3 equally spaced bicycle spokes. Let's try this. What's the fourth root of 16i? Let me draw this picture again for you, and then it'll make it, I hope this will be burned into your brain. Okay, 16i. Well, that's 0 plus 16i, fourth root. But now let's think about this as a complex number in the plane. Let's say this is 16i right here. That's 0 plus 16i. That's also a radius of 16 and an angle of 90. So I can write that as 16 cis 90. If you don't like that abbreviation, cis 90, then just write out with the parentheses cosine 90 plus I sine 90. But that's a lot of extra writing. Now, how do I take the fourth root? I take the fourth root of 16, which is 2 to the fourth of 16. But now, what angle do I use instead of 90? I take 1/4 of 90. Well, that's not a convenient angle, but half of 90 is 45, and half of 45 is 22.5. So this is 22.5 degrees. This is the fourth root of 16i. All I did was take 16 to the 1/4, and I took the angle 90 and divided by 4. But now let's draw this on a picture. I don't want 1/4 root. I want 4 fourth roots. So let's draw, 45 would be about right there, right? 22.5 degrees be about right here. So let's consider that to be 2 units long. I don't want to litter my picture. And an angle of 22.5 degrees. Now here's the punchline. I want 4 fourth roots. So I need 4 equally spaced bicycle spokes. Now that's 22.5. If I go, what is 360 divided by 4? Is 90 degrees. So I go every 90 degrees. I make another bicycle spoke here. It's 2 units long. I don't think I drew that beautifully. I make another bicycle spoke here. It's 2 units long. I make another bicycle spoke here. It's 2 units long. That looks a little scraggly. Okay, but let's name the angles. What's 22.5 plus 90? 112.5. And the radius, same radius, 2 cis 112.5. What's 112.5 plus 90? 202.5. Cis 2. 2 cis 202.5. And this fourth one, get 90 more. That's 292.5. 2 cis 292.5. Notice if you add 90 to this, you'll get 382.5, but this is 360. So 382.5 would be back on 22.5. Here are the fourth roots of 16i. 16i is like way, now these are all lengths too, right? So 16 is way up here. I drew 16i in that picture. Let me try it one more time. With a square root. Because your original question was a square root. What's the square root of -4? Now, originally in your math class, you were told you were forbidden from doing that. But now let's think of -4 as a number in the complex plane. 1, 2, 3, 4. Over here. Now that is what? 4 units long with an angle of 180. So that is 4 cis 180. What's the square root of that? I take the square root of 4, which is 2, and I take half of 180, which is 90. So I get this number right here. 2 cis 90. But you and I know 2 cis 90 by its location on the axis. That's actually 2i. Now I have to do how many bicycle spokes? Square root 2 bicycle spokes. I want 2 square roots. And that means I have to make 2 equally spaced bicycle spokes. Well, it's a bicycle wheel spokes. It's a terrible bicycle wheel. I've never even seen that. I've seen bicycle wheels with 5 spokes, but not 2 spokes. But where is the 2 spokes? They're going to be separated by 360 over 2, which is 180 degrees. And there's the 180 degree separation. So this next number right here in trigonometric form will be 2 cis 270. But in standard form, 2 cosine 270 plus I, need the parentheses, sine 270. That is 2 times 0 plus 1i, negative 1i. Sine of 270 is negative 1. So this is 2 times 0 minus 2 times I, or this is just minus 2i. That's how I normally name that point. So look at this. 2 spokes on the bicycle wheel for square root. 4 spokes on the bicycle wheel for fourth root. 3 spokes on the bicycle wheel for cube root. Let's take the 5th root of, just one more time. Let's do something odd like 60 degrees. So let's say half plus root 3 over 2i. What's the 5th root of that? Well, I got to recognize this 1/2 and root 3 over 2. That's the cosine of 60 and the sine of 60. So That is a 60-degree angle with a 1/2 side and a √3/2 side. Now the hypotenuse is always double, so double 1/2 is 1. So this is radius 1 and an angle of 60. I want the 5th root. I take the 5th root of 1, which is 1, and I take 1/5 of 60, which is 12. But now I'm going to repeat that. Sorry, slide up the paper. My fault. I'm going to repeat that 5 times. 5 times around this axis. Instead of 60 degrees, I'm going to start at 12, which must be very small. It always has a radius 1. 1 to the 1/5 is still 1. But what is that angle? 60 divided by 5 is 12. But now I need 5 equally spaced roots. So 360 divided by 5 is 72 degrees. So I just make 5 equally spaced things. Add 72, 84. Add 72, 156. Add 72, 228. Add 72. It's 290 and 16, it's 306. Add 72, which would be 368. I'm sorry. Add 72. 378. Somehow I'm adding 72 badly. 360 divided by 5 is 72, no question. 84, 156, 228. Oh, when I added 72 here, this is what? 330. 300 even, my fault. Add 72 to this, I get 300 even. If I add 72 to this, I get 372, which is 12 degrees past 360, which is back to the start. So here are my 5 answers. I guess I don't need to write 1 to the 1/5. And then let me link that to Austin's question he just posted. So my 5 answers are 1 cis 12, 1 cis 84, 1 cis 156, 1 cis 228, and 1 cis 300. I cannot make these into standard form easily without a calculator approximation because I don't know the sine and cosine of 12 degrees by a famous triangle. But I'm creating, let me see if I could draw 72 degrees. I'm creating a bicycle wheel with 5 spokes, 156 degrees, 228 degrees. It's hard to make equally spaced bicycle spokes, 300 degrees. These aren't perfectly equally spaced. This is 12 degrees, 84 degrees, 156 degrees, 228 degrees, 300 degrees. I'm speaking too long, so let me go on to the next question, but I'm trying to create that picture of 5 equally spaced roots. Start by dividing by 5, 60 turns into 12, and then build 5 equally spaced roots, all with the same radius. Okay. the question Austin has written in the chat there is the reverse of what we were doing. So let me write that on here. Make sure I'm numbering my papers. So I can post them later. Okay, good. So Austin asks the next question. And it's going to go back to the statement that I made right there. So if I have to raise, this is page number 5, 4 cosine 15, don't forget the parentheses, plus I sine 15. I'll write it out this time, but you can use the 4 cis 15 if you like. If I have to raise this to the 4th power, not the 4th root, but the 4th power, then what do I do? I have 4 cosine 15 degrees plus I sine 15 degrees. And let me use a different color to emphasize the 4th power. According to this rule, I raise the radius to that power and I multiply the angle by that power. Multiply the angle by that power. So I will get 4 to the 4th. That's the 4th power of the radius 4. And then I will get cosine of 4 times 15 degrees. That's a multiplication. Plus I sine 4 times 15 degrees. Now, as it happens, 4 to the 4th, if you like to check on your calculator, is 256. It's literally 16 times 16. But 4 times 15 for the angle is a sweet angle. It's 60 degrees, right? And I know the sine and cosine of 60 degrees. Cosine of 60 degrees is 1/2. Sine of 60 degrees is root 3 over 2. So actually, we could check this out on the calculator. 256 times 1/2 is 128. And again, here's 256 divided by 2 is also 128, but I got a root 3 right there. So there I've raised this number to the power. Now, by the way, because you know the cosine of 15 and the sine of 15, cosine of 15 is root 6 plus root 2 over 4. Sine of 15 is root 6 minus root 2 over 4. And if I multiplied both of those by 4, I just get root 6 plus root 2 plus I times root 6 minus root 2 to the 4th power. There's no way you want to do that with your fingers and toes. But I get this relatively simple answer. Let's verify it on the calculator. I'm going to check that I'm in degree mode. Okay, I'm in degree mode. I'm going to get a little calculator stand out. Okay, here's the calculator stand. First, let's type it in just like Austin gave it to us. And then we'll type it in this funky root form. So What happens if I take 4 times cosine 15 stop plus I sine 15 stop, and then close that parentheses, and then close the outer parentheses and raise it to the 4th power? I did have to use a lot of parentheses right there. In the calculator, I have parentheses around the 15. When I write, I don't always write parentheses around the 15. That's why you see an extra set of parentheses around each 15. What's the answer? 128 plus 2217 I. I bet you 128 times root 3 is that 2217025 stuff. 2217025 stuff. So that does say 128 plus 128 root 3. Calculator just doesn't write 128 root 3. Now, let's do it with a funky root notation here, where the 4's canceled out. And I got this. I should get the same answer, right? This will just be a pain to type in, but we're up for it. Root 6 stop plus root 2 stop plus I times root 6 minus root 2. Let me slide that over so I don't have so much shadow. Root 6 minus root 2. Okay, close that parentheses on the I, close that parentheses on the number, raised to the 4th power. Again, that took a lot of parentheses to write, but that's the same number of parentheses that I wrote here on the paper. Result? Exact same result as above. These two answers are the same answer. 128 plus 128 root 3I. So when I had that tiny, think about it like this. If you want to think about it as a wheel again, I have this 15 degrees and I have this thing that's 4 units long. What happens when I raise it to the 4th power? Well, 4 times 4 is 16 with a 30-degree angle. Now 16 is very hard to draw. And then 4 times 4 times 4 is 64. And 64 got another 15 degrees. Now 64 is 45-degree angle. 64 is way out here. I mean, that's not even realistic, but 64. Now I add another 15 degrees. My first one was kind of rough. And I get 64 times 4 is 256, which is way, 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 way out here off my paper at 60 degrees. So I started at 15 degrees, multiplied by 2, give me 30 degrees, multiplied by 2, give me 40, multiplied by 3, give me 45 degrees, and then multiply by 4, give me 60 degrees. I'm like casting a fishing line almost. I'm like grow, grow, grow. I'm growing and spinning that number until that number way, 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 way out here is 128 plus 128 root 3I, or you could say 256 cis 60. That's a little bit shorter if you use that abbreviation. I like this analogy, like you're casting a fishing line. You know, you just, no, it's kind of like casting a fishing line up, but usually you're casting a fishing line out. Like you hold it, if you're fly fishing, which, and I'm not a fisher person, but I've fished a little bit. You know, you hold the reel back and then you release the hold on the wire and just snap your wrist out, and the fishing line flies out and then drops in the water. Reel it back in, hope to catch fish. Okay, that's kind of the way you could feel about it in your mind, the picture you could create in your mind. Taking roots is like making spokes on a bicycle wheel. Raising a number to a power is like casting out the fishing line there. You don't have to draw the intermediate steps. You don't have to draw anything. You just have to execute the steps we did there. Okay, that's a good question. Like just filling in little patches of your mind with useful pictures. Throw something else at me if you're still thinking about it. Excuse me. Keep all my papers in order here. Which part of the universe are you interested in? According to the Hitchhiker's Galaxy, isn't the answer 42? It's just a kind of science fiction farce book. And they made TV shows out of it, stuff like that, but it's kind of also kind of very, very British humor. So if you have a chance, maybe you want some relaxation over the break, read this book. The Hitchhiker's Guide to the Universe. It's very British humor. It's sometimes very funny, and sometimes you say like, I didn't get that. You're like, what are they saying? But maybe there's a couple laughs in there. The author, if you're trying to look this up, Amazon, Barnes Noble, whatever, was Douglas Adams. I can't remember that's 1D or 2D. I think it's 1D. And that was just a running joke inside that book. What's the answer to life, the universe, and everything? And also 42. Also, by the way, 42 is Jackie Robinson's number with the Dodgers when the Dodgers first brought Jackie Robinson in their major leagues, broke the color barrier. So 42 is kind of a fun number. There are lots of sequels to this book. I read them. I don't recommend them. This one was funny. After that, it seemed to get tired to me. But maybe that's because I don't understand British humor. I like Doctor Who a lot, though. So I don't endorse that answer. That's just what I've heard. What else? And you guys got other things to do. You don't have to hang out, but if you want to, just relax, take your time, hang out, page through your book. If you got another question, throw it up. Again, I'm just sorting and cleaning papers on my desk here. So you take your time. Uh, that no problem, Austin. You're welcome to come and go. And if Stool's got another one, he's welcome to bring it up, or you guys can both come and go as you like. You remember, you can send me an email even this last week, and I'll get to you as quick as possible, but I usually turn them around fairly. I also check the XYZ homework in case someone posed a question there, which I usually answer too. Sometimes I'm a day late on that because I forget to check it. But if you want fastest service, I always send an email directly to me. But either way you want to do it. No problem. 3 minus. Let me look one up, no problem. Now, to do that, let me log in here and we'll flash one, we'll flash them on the screen. You tell me which one is you're most interested in. So first let me log in. Zoom, 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 zoom. And let me pull up the problems for 6.2. Got it, got it. And let me expand that window and share it with you. And then you tell me which one you like best. And then we'll write it on the paper too. Okay, so that's a starter. Question one's kind of a starter. And mine might look a little bit different than yours does, but it probably looks similar. Question two, let me just zoom through these. And if you have one in front of you, you can just point to it. 4, 5, don't look bad. 10. What about 10 there? Unless you have an objection, I'm going to pick that one. And if you like to pick another one, that's fine too. But I got 8 sine squared x, 8 cosine x equals 10. How do you solve that? And they want the answers from 0 to 2 pi. So they want answers in radians, but just one trip around the circle. And let me go back to my paper now and see if I copied it right. Sure, copied it right. Okay, let's try it out. So if I was looking at this problem, the reason I picked this out is because you have sine and cosine. That's like they're not working together. They're not helping each other. If I can, I'd like to write this as just cosine or just sine. Now I remember in the back of my mind that sine squared x plus cosine squared x is 1, always. So I could replace the sine squared x with 1 minus cosine squared x. And then I would have something just cosines. And then maybe, since I'm squaring, maybe I could factor quadratic formula, something like that. So let's replace 8 plus 8 cos x equals 10. Let's replace the sine squared with 1 minus cosine squared x. I got to clean this up a little because I'm going to get some things that change. I don't like to have a square leading with a negative, so but let's write this out. 8 minus 8 cos squared x plus 8 cos x equals 10. I think what I'd like to do is, remember, if you're looking at a quadratic equation, you want to set the whole thing equal to 0. And I want to get rid of this minus sign here. So I think I'm going to ship these 3 people over to the other side. And that means subtract 8. 10 minus 8 is 2. Add 8 cos squared x. That'll be 8 cos squared x. Subtract 8 cos x. And the 10 minus 8 again was plus 2. Okay, now I'm solving that for 0. So I wish it factored. To me, it does not look like it's going to factor. Now, there's a common factor. Everybody got a 2 inside it, right? So I could make my life slightly easier by dividing everybody by 2. Minus. But this still doesn't factor. Remember, I'm thinking like the cosine x is a variable u. 4u squared minus 4u plus 1. And I could test that for a little while, but that doesn't factor. So if that doesn't factor, I have to pull out the quadratic formula. U equals opposite of b plus or minus the square root of b squared minus 4ac over 2a. Remember, that's the quadratic formula. And then if I find out what that is, then I could say cosine is the, ux is the inverse cosine of u. So let's figure out what this u is. In this problem, the a is 4, the b is minus 4, respect the signs, c is 1. So if I insert those here, I get minus 4 plus or minus the square root of minus 4 squared minus 4 times a times c, 4 times 1, that's not so bad, over 2 times a, 2 times 4 is 8. So let's clean this up. 4 plus or minus 16 is negative 4 squared. Oh my gosh, it did factor, and I missed it. I totally missed it. Look at this. 16 minus 16. Do you see why I said that factored? Because that comes out to be square root of 0. That's just 1/2. There is no 2 answers, just 1/2. So I totally missed this. This factored into 2u minus 1 times 2u minus 1, which is 2u minus 1 squared. Now, I'm not nearly done, but at least it's not got crazy answers. The answer is this is just 1/2. Now, the good news is, even though I totally missed that factoring, the quadratic formula saved me, still gave me the right answer. So what I have here is 2 times the cosine of x minus 1 squared equals 0. Remember, the cosine of x is like the u. Let me slide that down. So that means that this thing inside here, 2 cosine x minus 1, has to be 0. The only number that I square and get 0 is 0 itself. So this animal here better be 0. This 2 cos x minus 1 had better be 0. I have no choice. But that means, sorry, I forgot my little x right there. That means 2 cosine x is 1. And that means that the cosine of x is 1/2. Now be careful, between 0 and 2 pi, there's two angles that have a cosine of 1/2. And that is 60 degrees, which I can write as 1, 2, and root 3. I think in degrees, but he wanted the answer in radians, right? We'll fix that. And then I have minus 60 degrees if I go 60 degrees down. Now, remember, he wanted answers between 0 and 2 pi. So 60 degrees is pi over 3. But I don't want to say minus pi over 3 because that would not be between 0 and 2 pi. So instead of thinking minus pi over 3, let's think the other way around. 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Those are the two answers to this problem. Okay, so let me just summarize quickly because we've got to wrap it up here. Here's a problem. I wish I was using the same thing, so I replaced the sine squared with cosine squared. I got to clean it up. I got down to this thing, this quadratic equation with a cosine x instead of a x or a u. It actually factored, but I missed that. So I pulled out the quadratic formula, and the quadratic formula saved my bacon. So either u is 1/2 and the cosine x is u, or I can think of this factoring. Either u is 1/2, cosine x is u is 1/2, or I could just say I'm solving this factoring. 2 cosine x minus 1 is 0, 2 cosine x is 1, cosine x is 1/2. Same way, same difference. I know that there's two angles between 0 and 2 pi that have a cosine of 1/2. I draw both of them. Even though I think in degrees often, they wanted the answer in radians, and they wanted the answer between 0 and 2 pi. So I had to fix the second one between 0 and 2 pi. Okay, good deal. Sorry. This was page 7. Okay, I'm going to scan these. I'm going to get my recording posted. You wrap up the XYZ. You pick up the exam tomorrow night and just scan it. And then Wednesday morning, sketch out what you'd like to do, find some problems in the book. And then Wednesday around lunchtime, you can come back and we'll answer some more questions. So no problem. You're welcome. You have a nice day, and I'll see you on Wednesday.